우주에는 아주 다양한 외계 행성들이 있습니다. 그중 가장 이상한 곳을 꼽는다면 저는 개인적으로 J1407b라고 생각하는데요. J1407은 센타로스자리 방향으로 430광년 거리에 떨어진 아주 어린 별입니다. 2007년 놀랍게도 천문학자들은 이 별 주변에서 지금껏 본 적 없는 아주 이상한 천체를 발견했죠. 당시 관측에 따르면 별 앞으로 아주 거대한 무언가가 빠르게 가리고 지나갔습니다. 그리고 당시 천문학자들은 이것이 아주 거대한 고리를 갖고 있는 토성 같은 행성이라고 추정했죠. 고리의 지름만 1억 8천만 킬로미터에 달합니다. 비교하자면 태양에서 지구까지 거리가 1억 5천만 킬로미터인데요. 이 정도면 토성의 고리보다 200배는 더 크다고 볼 수 있죠. 이 행성은 처음 발견한 천문학자 이름을 붙여서 마마제게 행성이라고도 부르죠. 그런데 최근 몇 년 사이 이 외계 행성은 다시 천문학계 뜨거운 논쟁의 중심에 서고 있습니다. 2007년 이 외계 행성이 처음 목격된 이후 천문학자들은 또 다시 행성이 별 앞을 가리고 지나가는 순간을 기다리고 있는데요. 그런데 현재까지 이 외계 행성의 두 번째 트랜짓은 목격되지 않고 있습니다. 처음 발견되고 나서 15년이 흐르도록 외계 행성은 보이지 않고 있죠. 그렇다면 과연 이 외계 행성은 어디로 사라진 걸까요? 오늘은 특별히 이 외계 행성 실종 사건에 대한 자세한 전말을 들어보기 위해서 2007년 이 행성을 처음 발견했던 장본인 나사의 에릭 마마젝 박사님과 인터뷰를 진행했습니다. 이 마마젝 행성의 실종 사건에 대해 이 행성을 처음 발견했던 장본인 마마젝 박사님은 어떤 생각을 갖고 있을까요? 그리고 대체 이걸 어떻게 설명할 수 있을까요? 우주먼지 현자타임즈, 정말 우연히 찾아왔던 행성의 발견 순간부터 최근의 논란에 이르기까지 아주 다이나믹한 이야기를 소개합니다. J1407 또는 V1400으로 불리는 이 별은 아주 역동적인 어린 별입니다. 그래서 별 자체가 밝기가 요동치는 변광성이기도 하죠. 당시 천문학자들은 그냥 단순하게 태양계 주변 가까운 별들의 밝기 변화를 모니터링하고 있었습니다. 당시에 사용했던 관측 데이터는 슈퍼 와습 관측을 통해 얻었는데요. 이 논란의 별도 역시 당시 관측되었던 수많은 별들 중 하나였죠. 보통은 별 표면의 어두운 흑점이나 별 앞을 주기적으로 가리고 지나가는 작은 행성으로 인해서 별빛이 미세하게 변화하는 것을 감지했습니다. 그런데 놀랍게도 별 J1407은 너무나 이상한 밝기 변화 패턴을 보여주고 있었죠. 2007년 4월 초 별빛은 급격하게 어두워지기 시작했습니다. 5월경엔 거의 별빛의 95% 가까이 어두워졌죠. 그러다가 다시 6월이 되면서 별빛은 원래 밝기로 돌아왔습니다. 보통 행성은 별에 비해서 훨씬 작습니다. 행성 하나가 별을 가려봤자 전체 별빛의 0.1, 1%만 어두워질 뿐이죠. 그런데 전체 별빛의 95%까지 어두워진다니 무언가 엄청 거대한 것이 별 앞을 가리고 지나갔다는 뜻이었습니다. 그런데 이상한 건 이뿐만이 아니었습니다. 2007년 4월부터 6월 사이 별빛의 밝기가 변화했던 패턴을 보면 중간중간 어두워지다가 갑자기 다시 밝아지다가 또다시 갑자기 어두워지다가 밝아지는 아주 지글지글한 모습을 보입니다. 게다가 놀랍게도 그 모습은 대칭적이죠. 2007년 4월에서 5월까지 별빛이 어두워질 때의 패턴과 5월에서 6월까지 별빛이 밝아질 때의 패턴은 정확하게 데칼코마니처럼 대칭적입니다. 이를 통해 당시 에릭 마마젝의 연구팀은 아주 거대한 고리를 갖고 있는 행성이 별 앞을 가리고 지나갔다고 추정했죠. 토성고리도 보면 단순히 납작한 하나의 커다란 원반이 아닙니다. 중간중간 고리 사이의 빈틈, 간극이 벌어져 있죠. 연구팀은 이 거대한 고리에도 중간중간 빈틈이 벌어져 있을 것이라 생각했습니다. 두꺼운 고리가 별을 가릴 땐 별빛이 어두워 보이다가 중간에 빈틈 사이로 잠깐 별빛이 들어오면 별이 다시 밝아 보이는 이런 복잡한 패턴을 그릴 수 있죠. 게다가 데칼코마니처럼 패턴이 대칭적이란 사실 역시 거대한 고리일 가능성에 힘을 실어줍니다. 이 행성을 두르고 있는 거대한 고리 사이 빈틈은 그 속에서 고리 물질이 반죽되고 위성이 만들어지며 생긴 흔적일 수 있습니다. 실제로 토성 주변 고리 사이 간극에서도 작은 위성들의 궤도가 그 빈틈을 채우고 있죠. 특히 중심별이 2천만 년도 안 된 아주 어린 별이기 때문에 이제 막 태어난 어린 행성 주변에 한창 위성들이 반죽되고 있을 가능성도 있습니다. 아직까진 외계 행성 곁을 도는 외계 위성의 존재까진 명확하게 검증된 적은 없습니다. 만약 이곳이 정말 거대한 슈퍼 토성이라면 외계 위성의 존재를 간접적으로 보여주는 중요한 증거가 될 수도 있지요. 당시 분석에 사용된 슈퍼 와습 관측 데이터에선 이 놀라운 슈퍼 토성에 의한 트랜짓은 딱 한 번만 관측되었습니다. 하지만 천문학자들은 이 행성의 독특한 모양 덕분에 행성의 공전 속도까지 알 수 있었는데요. 거대한 고리를 함께 거느린 채 별 앞을 가리고 지나간 덕분에 별빛이 변화하는 패턴이 얼마나 빠른 속도로 진행되었는지를 알 수 있습니다. 그리고 이를 통해 행성이 우주 공간을 떠다니는 속도까지 알 수 있죠. 당시 천문학자들은 이 외계 행성이 중심별 주변 대략 3에서 15년 사이의 주기로 돌고 있을 거라 추정했습니다. 물론 단 한 번의 트렌즈만으로 유추한 결과이기 때문에 오차가 조금 크긴 합니다. 어쨌든 정말 별 주변에 붙잡혀 궤도를 돌고 있는 외계 행성이 맞다면 그 다음 주기가 되었을 때 외계 행성은 또 다시 별 앞을 가리고 지나가는 모습이 관측되어야 할 겁니다. 그리고 천문학자들은 그 다음 트랜짓을 계속 기다렸죠. 그런데 난감하게도 이 외계 행성의 두 번째 트랜짓은 목격되지 않고 있습니다. 행성의 공전 주기로 추정되었던 최대 예측치가 15년이었습니다. 그런데 지금까지 15년이 넘도록 다음 트랜짓은 보이지 않고 있죠. 이 미스테리를 풀기 위해서 2018년 다른 연구팀은 미래가 아닌 과거의 기록을 뒤져봤습니다. 무려 디지털 관측이 있기도 훨씬 전 사진 관측만 했던 1890년대 데이터까지 모두 샅샅이 뒤졌죠. 이 별을 관측한 역사 속의 모든 관측 데이터를 다 뒤져본 겁니다. 하지만 과거 130년에 걸친 관측 데이터에서도 별은 그저 평범하게 빛나고 있을 뿐 또 다른 급격한 트랜짓은 과거에서도 확인할 수 없었죠. 그래서 최근엔 아예 가시광 빛이 아닌 적외선 또는 밀리미터 파장의 전파 관측을 통해서 이 사라진 외계 행성을 찾는 시도가 있기도 했습니다. 설령 이 미지의 행성이 지금은 별 곁에 있지 않고 멀리 벗어나 어둠 속에 숨어 있더라도 적외선이나 전파 파장에선 흔적을 남길 수 있기 때문이죠. 칠레의 전파 망원경 알마 그리고 초거대 망원경 VLT를 통해서 적외선 관측을 함께 진행했습니다. 천문학자들은 별 J1407 주변 행성이 돌고 있을 거라 추정되는 궤도 범위 이내에서 또 다른 천체가 있는지를 확인했는데요. 하지만 그 어떤 것도 보이지 않습니다. 그런데 더 재밌는 건 예상 궤도 범위를 훨씬 벗어난 별에서 먼 거리에 떨어진 곳에서 적외선 빛을 희미하게 내고 있는 또 다른 천체를 하나 발견했다는 거죠. 이건 중심별에 붙잡혀 있는 천체라고 보기 어려운 아주 먼 거리입니다. 이 새로운 발견으로 일부 천문학자들은 당시 발견되었던 J1407b가 실은 별의 중력에 붙잡혀 곁을 도는 외계 행성이 아니라 훨씬 가까운 거리에서 우연히 배경별 앞을 가리고 지나갔던 떠돌이 행성일 수 있다고 추정합니다. 물론 이 역시 가능성은 높진 않은데요. 이렇게나 희한한 행성이 정말 우연하게도 딱 별 앞을, 그것도 그리 멀지 않은 비교적 가까운 거리에 놓인 별 앞을 가리고 지나가는 순간을 딱 놓치지 않고 지구에서 관측했다는 건 정말 엄청난 우연이 겹친 결과이기 때문입니다. 2007년 이 별의 이상한 밝기 변화를 처음 발견했던 장본인 나사의 에릭 마마젝 박사님은 이 마마젝 행성의 실종 사건에 대해서 어떻게 생각하고 있을까요? 직접 그의 이야기를 들어보겠습니다.
First, could you please give me a brief introduction about your famous discovery an exoplanet with a large ring system?
So late in 2010, my graduate student Mark Pico and I were investigating young stars in the nearby OB association Scorpio Centaurus, and we were searching for new young sun-like stars, about 10 million years old. And we saw an email that the SuperWASP Consortium, which is a planet-finding group, released a large amount of their data, made their archival data available. And I asked Mark, I said, why don't we cross-reference our young stars with the SuperWASP archive data? And I said, we can measure rotation periods because most of these young stars should be very active. Their brightness should change. It should be very easy to measure the rotation periods. So I thought, oh, maybe this will make an interesting, chapter or paragraph in the thesis project he was working on. And he did, and he came back into my office the next day. He had a whole bunch of printouts, and he said, well, we have light curves for dozens of these. And I said, let me guess, the rotation periods are all between, fraction of a day and about 10 days. And that's typical for young stars. And he said, yeah, they all look like that. They all look like sinusoids, except this one. And that was the original J1407 plot. And it showed, yes, it was variable every 3 days. And then there was this huge dropout in spring of 2007. And it lasted for weeks and weeks. And the light curve was very messy. And we went, oh, that's interesting. It didn't look like any other young light curve I had seen. We thought we better follow this up. So I put tape on it and I put it on my wall so I wouldn't forget it because I was still at the end of a semester. I was still doing teaching and exams. We started to follow it up. He was finishing one of his thesis papers. So I started digging into it a bit, and we found that there was another instrument called the ASAS, the Automated Sky Survey, another robotic telescope in Chile. And they had some data for it, and they showed the big dip There was much less coverage, but it was clear the dip was real. It was not an instrumental effect. And so we were zooming in on the SuperWASP data and zooming in on the ASAS data, and it was clear that this was something very strange. And so I had, other students looking for projects, and so I had another student, Fred Millikamp, who was looking to write a code to model this. I said, let's model this. The thing that came to mind was it reminded me of the discovery of Uranus's rings. Back in 1977, the planet Uranus passed in front of a star, and the Kuiper Airborne Observatory was deployed to the southern Indian Ocean, and astronomers were observing the brightness of the star for a few hours before Uranus passed it and a few hours after, and it was a surprise. They did the experiment to study the atmosphere, but what they discovered was the rings of Uranus. There was dips both before and after the primary occultation, and that was the discovery of Uranus's rings 9 years before Voyager 2 passed Uranus. It reminded me of that because if you look at the dips, it's a little bit symmetric. There's features on both sides that look very similar. You kept zooming in and you kept convincing yourself that we were seeing, two arms or two, maybe it was a ringed system. It was somewhat symmetric. And whatever it was has to be huge. You do some back of the envelope calculations, the system would have to be enormous. And it was a young star, and there certainly had been other young stars that had seen dipping phenomena, but it was mostly the inner edges of protoplanetary disks or accretion events or something, but this seemed to be a very discrete phenomena. There was years and years where the star was doing nothing except rotating with star spots, and then there was this 50-ish day period in 2007 where up to 95% of the star's light had blocked out. And so that's what first caught our interest. I mean, this was a total surprise. We were not looking for this thing. It took about a year to write up the results. And I just went around asking my collaborators, I said, well, what do you think of this thing? What do you think of this thing? And people said, oh, I can help. I can do this. They were helping with some of the analysis. But it was a very strange object. And I think the field was not ready for it. Anyway, we'll talk more about it. But it was clear that it was something massive. It was very opaque. It had to be, much, much bigger than something like a Saturn. And so the first thing that came to mind was maybe this was a circumplanetary disk. Maybe this was a moon-forming disk around a 10 or 15 million-year-old star. And that would have been the first one that had been seen. Such disks have been imaged since directly in the last, 5 years or something. But we thought, well, maybe this was the first one that had been detected, blocking out the light from a star.
So my next question is that, is the planet J1407b simply a Saturn-like planet with an unusually large ring, or is it a smaller version of protoplanetary disk?
Well, that's a good question, and we don't know. We don't know whether we did not see the central object past the star. All we saw was the outer part of this, and we've been calling it a ring system because I'm not sure what to call it. It clearly is not a uniform annulus. It's thicker and much larger than Saturn's rings. It's very small for protoplanetary disks. Protoplanetary disks are typically tens to hundreds of AU in size, although more recently people have seen some smaller disks of AU scale around brown dwarfs and low mass stars. But there's a lot of features in it. There's places in it where the gaps are very clean, and that had not been seen before in these occulting bodies. So the answer is we don't know. We don't know if it's a young planet. We don't know if it's a brown dwarf. We had initially assumed it was in orbit around the object. Now, we didn't see a second transit. We still have not seen second transit. And we've had students look into archival data, and we've been taking new measurements over the last decade. There's been no evidence of a transit since over the past 15 years. And we have archival data going back to the 1890s. There was some images, photographic images, hundreds of photographic images that have been scanned in going back to the 1890s. And there's been no hints of any phenomena further back. So what we seem to have ruled out, it looks like anything with a period less than about 10 to 20 years, we've ruled out pretty completely. So it's becoming more and more likely that it might be a rogue object. And we thought that would be very unlikely because the star is, it's not super nearby. I think it's around 120 parsecs away, maybe 400 light years, which sounds far, but there's not a lot of distance between to randomly have a star or brown dwarf pass in front of. The speed at which the object was passing in front of the star, we actually have an estimate of how fast it was passing in front of the star if they're at the same distance. And that's because there are places in the light curve where the brightness changes very rapidly, and it almost looks like a knife edge. It almost looks like you have something completely opaque covering the star. And there's places in the light curve where the light just seems to drop out. And since we know the size of the star is very similar in size to the sun, on the order of 1 million kilometers, we can estimate that velocity. And the number you get is about 30 kilometers a second. Wow, 30 kilometers a second. That sounds like a nice orbital velocity. That is how fast the Earth takes to go around the sun. So if this object was at 1 AU, it might make sense. But if it was at 1 AU, the period would be around a year. And we can rule out easily a period of a year. The period has got to be much, much longer. It's got to be more like decades or longer. And that presents a challenge, because it's very, very difficult to get a velocity as high as 30 kilometers a second and still have a period that long. The orbit has to get very, very eccentric, very comet-like. And then you say, well, how stable could a ring system be on such an eccentric orbit? And so you start to run into dynamical problems. And the dynamical problems become so extreme that Stephen Ryder and Matt Kenworthy also concluded in the mid-2010s. They said it might even be more plausible that the disk is counter-rotating. It's retrograde, which is even, you have to get more and more complicated models to start to fit the data to make it a bound object. But nowadays, I'm not so sure. I mean, it has been very confusing, and it's been difficult to get better and better follow-up data. We have an ALMA detection from a few years back, millimeter detection. There is an object, nearby the star that has a brightness somewhat, similar to what you might expect if it was a circumplanetary disk of, an AU in size around a substellar object, 10 or 20 Jupiter mass object that was 10 million years old. The predictions match pretty well. The problem with ALMA is you need multiple images of the sky, because the millimeter sky is brand new. Most of the places you look have not been looked deep in millimeter. So there's little, just like the background on your image with all those galaxies, everywhere you look, there's millimeter emission from background galaxies. And so really what we need to do is see something moving. And we've not been able to get follow-up. We've been putting in proposals and not getting them accepted. So, we're still trying to get follow-up observations to constrain it. But the interesting thing is there is a source at a distance from J1407 that would be consistent if it was an unbound object moving at about 30 kilometers a second. But if it's unbound, it's almost certainly completely unrelated to the star J1407 itself. Some people have said, could this just be a young planet or brown dwarf that was ejected and has a disk in the same group, in the Scorpio-Centaurus association? And the answer is very unlikely, because the velocity would be so high it would not stay in the group for long. Most of the stars in SCO-SEN, their velocities are within about 1 kilometer per second of each other. This thing would be moving at 30 kilometers a second. And if it got ejected at that speed, it probably would have lost its disk anyway. So if it's a rogue, it's probably unrelated to J1407. There's no need for it to be at the same distance or ring or whatever it is. It's a mess, whatever it is, but it has gaps in it, and it's probably on the order of 1 astronomical unit in size. If it's unbound, it's interesting, because then you have to say we randomly saw a planet or brown dwarf with a 1 AU scale disk randomly pass in front of a star. Now that's crazy. How has nothing like that been seen before? We have, again, that's looking at a star only 400 light years away. We've had surveys of the galactic bulge for years, looking for microlensing events, eclipsing binaries. There has been surveys looking at millions and millions of stars, and nothing like that has been seen before. And the further you look and the denser the star field, you would expect to see more and more of them. So if there was objects like that, if it was common for rogue planets and brown dwarfs to have, we should have seen them towards these deeper and denser surveys. So it's a mystery. It's the object interesting if it's bound to J1407. It's very interesting if it's unbound. Perhaps more interesting if it's unbound for J1407. Whatever it is, it's not a clear-cut case. I don't want to give the impression that it's a clear-cut case of a planet. It really is it's very nebulous. We don't know what the central object is. We think it's less than, probably less than 10 or 20 Jupiter masses. It's probably planetary scale, but it could be a low mass brown dwarf as well. We have not seen the light from the central object. It's just this. We're inferring the properties from this massive material and the scale of that ring/disk system.
Then is it possible to say the high eccentric orbit of this planet may be one of the plausible reason of this mystery of missing of this planet.
It could be. I mean, if it's bound to J1407, the star, it has to be on a highly eccentric orbit. And then it's interesting that the system could even maintain a disk of this size and be on such an eccentric orbit. I don't have the eccentricity constraints right now off of the latest analysis. It's just the periods are likely to be more than 10 or 20 years, and the velocity we saw is typical for 1 AU. So that the eccentricity would have to be at least tenths, but might be very high. I don't know, pushing 0.5 or 3/4. But it also becomes very unlikely. Then we would have to be catching the transit of this ring system during its periastron, and that's statistically unlikely. You're more likely to catch a transit while the object is slow moving, but then again, it's further out. So geometrically, it's also lower probability. But statistically, the object would spend less of its time near its periastron.
Then do you expect the next transit will eventually be confirmed by further observations?
I think it's 50-50 at this point. I think honestly, it's either it could. This object has been surprising. If it did, it means the orbit is extremely eccentric, but it is bound. And then I would say it's almost certainly a circumplanetary disk. And we're seeing it at high resolution. And when it passed in front of the star, we were seeing what does a circumplanetary disk look like? What does the optical depth of the dust look like in very fine detail? Maybe it's a moon-forming disk. That would be amazing. If we don't see it pass in front of the star again, and I would give 50% chance to that too, then it was a rogue object and it was a one-off. And so our only hope is to try to image it very deeply, again with ALMA, perhaps with something like JWST or additional adaptive optics imaging. It still needs time to move further and further away from its star.
Then if that object was really a ringed planet, then how is it possible for a stable and large ring system to exist beyond the Rush limit of that planet?
So it's different from the case of rings like we see for the solar system planets, for Jupiter, Saturn, Uranus, and Neptune. That's a dynamical instability. If you put a moon or something too close to the planet, it will be tidally torn apart and you will get a fine ring of material. I think this is a different case. It's clearly large enough, just back of the envelope, it should be on the order of tenths of an astronomical unit to something like a 1 astronomical unit in size. That is a totally different scale. And that starts to become of the scale of the Hill radius of the planet. And clearly we see moons have formed around the giant planets in our system. Look at the Galilean satellites of Jupiter, the large satellites in Titan around Saturn. Clearly there was circumplanetary disks early in the history of our own solar system that spawned moons similar in size to our moon around the giant planets. Those were much larger. Those are much larger than the Roche radius. And material was fed in through the Hill radius from further out, from the sun's disk. There was material orbiting the sun that when it spiraled in and got close to the planet, it got pulled into the Hill radius of the planet, and the planet formed its own subdisk, its own circumplanetary disk. And that material fed onto the planet. It's a very inefficient process. Look at Jupiter, look at Saturn. The vast majority of the material simply got accreted onto the planet, but there was probably, just a little bit of material left over. I'm not sure what the fraction is, 1 part in 100,000, 1 part in a million, something like that. A very small amount of the material would not have made it into the planet, because if there was much more material brought in, that gas and dust would have torqued those moons and caused those moons to migrate in. What we see in the solar system is the survivors. You're seeing the things that have survived 4.5 billion years. There could have been generations of moons before the Galilean ones, early on, that migrate into the planet. So we don't know exactly how long those disks survive. Typical disks around young stars last on the order of a few to 10 million years. We have pretty good constraints on those, studying young star clusters. There are cases of disks around brown dwarfs that have been seen up to 40 and maybe even 50 million years. So there's some evidence that disks may last longer around substellar objects. It may be more difficult for them to disperse their disks, but we don't know how long they would have survived.
These kinds of large ring system planet is very unusual, or maybe more common.
The thing with astronomy is you start finding odd objects and then you start finding lots more. I'm sure white dwarfs seemed unusual in the late 19th century. Pulsars seemed unusual in the 1960s. giant planets close to their star seemed unusual in 1995. I don't think this is going to be unusual. I think it's just the first case, and like a lot of things in astronomy, the first cases, sometimes it's hard to get enough data and explain what's going on. It may take a generation or two. There's cases in astronomy where we've had evidence of things for years and didn't even know what we were looking at. Like the case of polluted atmospheres of white dwarfs. We were seeing ground up asteroids orbiting other stars for a century and didn't realize that was giving us clues that planets had formed around those white dwarfs. Sometimes you get a sneak peek at what ends up being common. Then again, there's cases like the pulsar planets, the B1257 plus 12 system. Those were found very early, 30 years ago, arguably the first good, solid evidence of extrasolar planets, those pulsar planets discovered by Alex Volshin and Doug Frail. Those ended up being very rare. There has been, since then, there's been lots of surveys of pulsars, and that system seems to be a bit of a freak. So who knows? I think with more of these robotic sky surveys, more and more of the sky imaged repeatedly over and over and over in different bands to different depths, we're going to start finding objects in weird evolutionary states. Like Tabby's star, the Boyajian star as an example, that is probably debris around, an older, maybe 1 or 2 billion year old star. It's on a time scale, we may be seeing a phenomena that's happening over a very short time scale with regards to the age of the star, maybe something over the order of decades or centuries that's not common for other billion-year-old stars. Once you start looking at light curves for thousands of stars or millions of stars, we're going to start seeing stars in the act during things that are happening, and they're just going to appear as rare events that we catch during the time scale of a human PhD. So we shall see. I will say there are cases, there are so-called dippers. There has been some cases of things that didn't look like big ring systems, but things that look like if you put a coin in front of a star at an angle, or a dish and passed at an angle. And what you see is a light curve that looks like a lopsided letter V. You may have a very strong dip and then a very slow return. And you can get those with a very simple model of something that looks like a plate passing in front of a star. If there's no structure in that plate, it's just a very optically thick, you can get a very simple V-shaped light curve. And there are cases of those seen in Kepler light curves, but I haven't seen anything as complicated as J1407.
현재까지도 많은 천문학자들은 다양한 망원경을 통해서 기약 없는 다음 트랜짓을 기다리고 있습니다. 과연 말도 안 되는 우연들이 겹쳐서 아주 이상한 떠돌이 천체를 포착했던 것이 사실이었을까요? 아니면 한참 뒤에 그토록 기다렸던 두 번째 트랜짓이 관측되면서 이 논란이 끝날 수 있을까요? 실종된 외계행성 J1407b, 아니 외계 행성인지조차 확실치 않은 이 미스터리한 존재가 부디 멀지 않은 미래 인류의 망원경의 품속으로 돌아오기를 바라봅니다. 우주먼지 엔터타임즈, 오늘은 여기서 마칩니다. 구독과 좋아요도 부탁드릴게요. 우주먼지 여러분, 감사합니다. 안녕.